Experiment 7, Bungee Jump Accelerations from the Physics with Vernier lab book. In this experiment, you will use a low-G accelerometer to measure bungee jump accelerations of a wooden block, or in our case, we're going to use a doll to make things a little bit more realistic. Start by connecting a low-G accelerometer to LabQuest. Choose New from the File menu. Connect the low-G accelerometer to your wooden block or to your doll so that the arrow on the low-G accelerometer will point up during bungee jumping. In this case, we have the arrow pointing towards the doll's feet because that is the direction that she will be bouncing. Before suspending the doll, we need to zero the sensor. To do this, hold the sensor so that it is level with the arrow pointing up. It helps to hold it on the edge of the table so that you know that it is level. To zero the sensor, choose Zero from the Sensors menu. Suspend the doll from the ring stand. And make sure that there is enough cord so that the accelerometer won't get hung up as she jumps. You also want to make sure that as the doll bounces, it doesn't hit the floor, and that the cord has enough elasticity so that as it bounces, it doesn't bottom out. For the first part of this experiment, we will be investigating the bungee jump accelerations during the first bounce. We will start out by holding the doll up near the ring stand, letting go of the doll, letting her bounce, and then catching her at the end of the first bounce. Hold your doll up near the ring stand. Start data collection. Wait about a second, let go, and catch. When data collection is finished, your graph will be displayed. To examine the graph, tap on any data point. Notice that over on the right, accelerations and times are displayed. During the first second or so, notice that the accelerations are 0. That's because we zeroed the sensor and held the doll steady. Once we dropped the doll, she went into free fall. Free fall occurred during this part of the graph. So tap on any point along there, and the acceleration here is negative 9.78 meters per second squared, just about what we would expect. Once the doll started to accelerate upwards, notice that the graph changed dramatically. Then we caught the doll. In the second part of this experiment, we will investigate the accelerations during the bounces. To do this, pull the doll down about 5 centimeters, start data collection, and release. It's important to only pull the doll about 5 centimeters down and to release the doll so that she bounces straight up and down to get good data. After data collection is finished, your graph is displayed. Determine the point in the motion where acceleration is both positive in direction and has a maximum magnitude, which is right about there. Remember that this is an acceleration versus time graph, not a position versus time graph, so it's important to understand the relationship between the two. So this point right here, does this occur when the jumper is at the bottom, the middle, or the top of the oscillation? In the next part of this experiment, we will investigate accelerations during a full bungee jump. There are a couple of things to keep in mind when doing this part of the experiment. First of all, you want to make sure that you release the doll so that she bounces straight up and down with minimal rotation and side-to-side movement. You may also want to hold the cord of the accelerometer up and out of the way so that it doesn't get hung up on the ring stand or the side of the table. Depending on the elasticity of your bungee cord, you may also want to extend your data collection. In our case, we've decided to extend it to 5 seconds. Tap the word length on the meter screen. Change the data collection length to 5 seconds and tap OK. Raise the doll up to the ring stand, start data collection, wait about 1 second, and release. Examine the graph by tapping on the data points. Determine the acceleration at 8 different points on the graph, choosing points during the initial rest, free fall, when the cord is taut, and several bounces. Record those values in your data table and indicate the direction of the motion using up, down, or at rest. You may be surprised to see how well the data collected in the lab with the bungee jumping doll matches the actual bungee jumping data collected from a person jumping off a bridge. Some variations of this experiment include placing a motion detector on the floor and collecting position versus time and velocity versus time data at the same time as the data that's collected from the accelerometer. It's interesting to compare the graphs. You also may want to investigate the relationship between the mass of the bungee jumper and the acceleration. You can do this by adding masses to your doll or by using different dolls. Another variation would include attaching a force sensor to the ring stand and measuring the forces that occur during the bungee jumping.